for academics, and I hope to show that the registration piece is actually useful on the academic side too. The key there being the lightweight piece. But so where did this all come from? Back, see if I can put the slide back towards the end of 2022, I realized I have this slide that I show at the end, as part of every RDKit presentation, where I make a joke that there's no roadmap because I don't drive. And so we kind of don't know what we're going to do next from the RDKit, but there are some things that are fairly obvious. I've been showing a slide more or less like this for like 5 years. And the first bullet point on this all the time is to make sure that all of the pieces required to build a good compound registration system are there. And I realized around the end of 2022 that I've been saying this for years, and now I actually think everything is finally there. And so you could actually do this with the RDKit. And so I had no plans of doing it, and so obviously somebody else should do it. And I said this at a few meetings, and nobody did it. So I thought, well, maybe if I set an example and show how it can be done, then other people will take it up, and I don't have to think about it anymore. So this kind of led me to, well, maybe I should write something. Maybe I should actually do a registration system.
And that's where I came in, because I only started my PhD not that much after Greg had joined Serina's group. And you probably all know it at the beginning, you're very motivated, you start thinking about all your experiments, you start quickly writing down bits and pieces everywhere, and it escalates quite quickly. So you either end up with lots of disjoint Excel data sheets or some other version to keep track of what you've actually done. But actually, before I joined Serina's group, I was in a job where I had to work with quite a lot of databases, and we also did some migrations. So I knew what trouble I could get in if I ever was to migrate something. I quickly just jot it down in an Excel spreadsheet later on if I was growing my data as I got into my experiments. So coming from that, I started thinking, okay, maybe I could start to capture my metadata and my data that I actually collect over all of my experiments in a good and efficient way. So that was kind of the conjunction where we came together, because I was obviously also talking with Greg about it. So the idea was to capture the information about the molecules and the experiments together in a good way, in a structured way, but also not in a very bloated up system. So yeah, we both had the idea to maybe come up with a solution for this problem we both discovered. And this is where this talk will fit in. So we want a flexible system that will store experimental data and the metadata. But also you need to think about how you want to register the compound that are associated with the data that you are collecting. And I will be focusing more on the experimental data, and then later on Greg will take over and talk about the compound lightweight registration part of it. So if you start storing experimental data, they're kind of like the 3 parts that I was thinking about and that we wanted to capture. It was the molecules that I worked on. In my specific case, it was a data set where I only had one specific conformer for one molecule, and then my metadata to the experiments, and then my data that I would produce out of them. And technically, this is what I was also saying just now, you can structure that in 2 parts of the whole system. So the first one, the molecules worked on, kind of already implies that you have to have some notion of uniqueness of what you want to cover, and a registration key, which could be just a number if you want to think about it that way. And then the second part would be something in the form of a table. So if you want, that's still your Excel spreadsheet, if you want to think about it that way. And that could be linked via a key, let's say via that number, to my registration of the molecules. So yeah, I'm going to focus on the blue box. So normally, what do you think about when you think about your database layout? You think about, when you start looking at your metadata, what do I have to do as a configuration to be then later on able to produce that experiment? That is kind of what you would define as your metadata. So if you want to think about an example like conformer generation, it would be all the parameters you've set, like a random seed, whatever is in the parameter object, like what experimental affordance, etc. And then that metadata will be associated with a unique ID for each experiment. So I have another key there. And then the second table would be the results of the experiments run that I can link to my initial metadata table. And that would be the data that actually comes out of the experiment. And then also, because we don't want a bloated up system, large data files that might be an output, like if I in the end run something like a trajectory, I wouldn't put in this system, but I would maybe link to where I stored that data. So my database in the end is really my turning point where I can get all the information from, but it won't be the bloated up system of storing all the data ever associated with that experiment in there. If you then start thinking about your database layout and you've never done it before, there are two ways you can go. There's one, if you've never encountered something like that in design schemas, which is quick and easy. When you think about this is not my actual research, I just want a system that works. Or you could go more in depth and start about thinking what is the best possible way of capturing this in a table? How can different tables link to each other? And yeah, what's the best performance as well that I can get out of this? So I'm going to show you the quick and easy way that you could maybe also immediately adapt. But then there's also good news. You can start out quick and easy and then later on migrate to the more in-depth way. So if we want to stick to this table layout, the quick and easy way would be to use a JSON. So you don't have to think about what your different columns look like in your database system to begin with. You could just work with a Python dictionary and then put that flexibly in your JSON column in your database system, for example, Postgres. And then what you would also have in metadata would be your unique experiment ID, and then your date added, which would be the time, just a timestamp format. And your second table would then be the results that you want to cover, which would be your, again, a unique ID that you have with that, a result ID. And then it would be linked to an experiment UID, so the unique ID. But here in the second table, in the result table, that wouldn't have to be unique because you could have multiple runs, experiment runs run with the same metadata. So in the second table, your result ID would be unique key. And then you could also see here again with the lwreg node, you would have another key that would link to your chemical registration system, where you could then store the compound that you would actually work on. And then all the data could go into a JSON. So the JSON here is really the key to the flexibility part, where you don't have to come up with an elaborate schema or design at the beginning. You could later on suffer from some discontinuities if you do that. And also it's not as performant as if you would think about what your actual columns and what your type's going to be later on. But you could switch by taking out everything that's in the JSON later, and then go to a schema like this, where you have every column clearly defined. So the difference to the schema that I showed you before, that here is for every thing that went into the data column that was just a JSON before, here you have a separate column where you have the type also clearly defined. So here that would be, if I'm capturing conformer generation data, for example, the number of conformers that I get out. And if I'm tracking additional information like the number of conformers that I outputted, or information on the failure and how long it took, I would have extra fields for the time it took to embed and, for example, the initial coordinate training. But if you first started out in the JSON, you could introduce or add these columns later on and still keep your JSON from the original ones. So you don't have to come up with the perfect schema in the beginning. And then what's also the nice thing, if you work off these SQL-based databases in comparison, for example, to your Excel spreadsheets, is that you have a lot of power if you want to query your data and get information out of it, because you can formulate it in the nice SQL queries. And once you get used to the way of writing them, it's actually not difficult at all. And they're only 4 very basic functionalities that also are kind of only meant for the minimal example to show you the power of what you can formulate. So for a select, that seems quite basic. So that would just be a query asking for all the experiment UIDs and the random seeds from the experiment metadata table. Then with select count, you could always check how many entries do I have there in the experiment results table. Then you can get exact experiment UIDs where the local registration number is to. And then what is even more powerful is this join statement. So if you go back to your analogy of the Excel spreadsheets and you would have lots of different tables, but you want to join them together to then run a query in SQL, it's very easy to do if you have different tables to join them according to some restriction that you put in. So here, for example, it's join on the column experiment UID, and then you can put in additional query information like give me all the experiments back where I pruned with a pruning threshold larger than 0.5 and where I got more than 5,000 conformers back. And that would give you all the result IDs and all originals back here. So this is all about how you would store your data and metadata in your database setup. But what I still haven't talked about is this, how do I even define at the beginning a unique ID for a molecule or a conformer that I work with? And that's where the lightweight registration part comes in.
So the idea of this piece is we want to keep track of all of the compounds that we work with or that we're thinking about working with. To go into this so that we have these lwreg nodes that we can link our experimental data to. If we're just talking about storing things, that's kind of, you could have an SD file or a big spreadsheet or whatever. But you can also just think about storing, keeping track of the compounds we've worked with or are thinking about working with. That's exactly what you do with a compound registration system. So why not use a compound registration system for this? They're designed for it. The problem is most compound registration systems are these giant corporate things that you need enterprise licenses and they're a pain and just a mess. So we wanted to have something simple. The way I think about compound registration systems is they are inherently very simple systems. Their job is to answer 3 questions. So the first one is, have I seen this compound before? Is this compound registered? The next is, here's a compound, give me a key for that compound. And what that means, if it's there already, give me the existing key. And if it's not, put it in the system and give me a new key. And then the last question is, here's a key, give me the structure. And that's all a compound registration system needs to do, in my way of thinking about it. And if you want to argue about that, we can do that later over the beer. I'm happy to. And from a person who wants to build a software system, this is really stupidly simple, right? You just need to answer these 3 questions. It's really easy. You can imagine if you've done any system design, you can imagine what it looks like. There's a trick though. So the kind of questions we might want to ask these things are, which molecules were used to, sorry, let me get the laser. Which molecules were used to generate a particular result, or have I already done a calculation using a particular molecule, or was this molecule part of the training set? And all of these require us to be able to answer a question, are these 2 molecules the same? If you haven't worked with computers and molecules, this seems really easy. And if you have worked with computers and molecules, you know that this is actually fairly subtle and a giant pain in the ass. So I'm going to take a quick digression into the so-called simple world of molecular identity by asking you some questions. So get ready, it's a pop quiz. So are these 2 molecules the same? This is esomeprazole, or it's the API in esomeprazole. If you don't want to stare at it for too long, the difference between these 2 is one is a resident structure of the other. So on the left-hand side, there's an SO double bond, and on the right-hand side, it's this with our form. I think we probably would all agree that these are the same. If you represent this as smiles, they're different, right? If you're actually doing, if you want to put this into many docking tools, if you're not doing pre-processing, they're actually also different from each other. But generally, when you do your pre-processing, your standardization, you're going to clean this up and make them the same. But from a smiles perspective, these molecules are different. So it depends on how you're looking at them. So what about these 2? The difference between these 2 is they're tautomers of each other. So the right-hand side is a tautomer. The left-hand side, are those the same? That depends. If you put them in water, probably they're the same. If you crystallize them, you can actually crystallize these independently of each other, and you get different polymorphs. So you can isolate these 2 things. They actually are different from each other under some circumstances. If you put these into a fingerprint calculation, they're going to be different. Right? If you put them into a docking calculation, they're going to be different. So there's some contexts where they're the same and there's some where they're different. Here's another one. This one, the difference is the stereochemistry. Are these different from each other? Well, probably most of the time. Most of the descriptors we calculate with cheminformatics tools, they're the same, right? Most fingerprints are the same. Actually, in the body, they're kind of the same because one gets turned into the other. So that affects the dose, but actually they're both bioactive, even though only one of them interacts with the receptor. So it depends. Are these two the same? These are the same conformer, same same tautomer, same stereochemistry, et cetera, but they're different conformers of the same molecule. Those the same? Well, it depends, right? If I put them into, if I'm doing rigid docking, I'm going to get different results from those two things, right? If I calculate 3D descriptors, I'm going to get different results. If I do something 2D, obviously I'm going to get the same result. So the answer is it depends. So what I'd like to take out of this is that molecular identity is often context dependent. It's really not a simple question, even though it seems like a simple question. If you're going to limit yourself to a single context, it gets pretty easy again, right? So if you say, I don't care about tautomers, I don't care about stereochemistry, I don't care about 3D, then things get simpler. But if you start caring about those other things, things get a little bit complicated. So some of the things that make this non-trivial, we already saw, so resonance forms, charges, tautomers, there's counter ions and solvents, right? That can be important if you're pulling data from a public source or from an in-house database. You often need to know what the counter ion is. Sometimes you don't. Sometimes we strip them, sometimes we don't. If you're doing solubility, you probably don't want to. So I have an example in the backups, ibuprofen. The measured values of the solubility of ibuprofen change by 6 orders of magnitude, depending upon what the counter ion is. So it kind of matters. Other things, it doesn't matter. So again, sometimes we care and sometimes we don't, and it really depends upon the context. And if your registration system's sole job is to say, are these two things the same? If you have one way of saying that things are the same, your registration system needs to read your mind in advance to know every possible thing you might want to do with it. And that's pretty much impossible. So we need to figure out how to build flexibility. So that's the end of our digression. Now we're going to go back to talk about the registration system. Hopefully everybody is with me that this is maybe not as simple as it seems. So we saw this already from the system building perspective, that these 3 questions are simple. From a cheminformatics perspective, the have we seen this compound before is maybe not so easy. But what do we need to do if we want to answer that? We need to be able to standardize molecules to solve this, at least solve the resonance structure problem that I showed at the beginning. We probably want to filter molecules. So if I'm trying to put a system, let's say an organometallic molecule, into my database that really is only set up to handle small organic molecules, I probably should filter that out. Or if I try and put a protein in and I really am only set up to deal with small molecules, I probably want to filter that out. So we might want some filters coming into our registration system. Once we have the thing standardized and we actually want to keep it, we need to have some way of figuring out if the molecules are the same. And I'm going to propose we do that with hashes or keys. We'll talk about those in the next slide. And then we just need to store those structures together with the hash and the key. So now this hash and key is going to be doing a lot of work. We put together a system for doing this. It's called lwreg. I am really creative with my names. So LW lightweight, reg registration. It's in GitHub. It's open source. It's Python based and easy to integrate into any computational workflow. There's a command line client if you like those things, and I'll talk about some of the features the way. It's also under active development. So we're actually working on this, using it in the group on a number of different projects, and there's other folks using it. But let's talk about what it does. So the data flow in the system, molecule comes in, it needs to be parsed, obviously, so we need to take the mole block or the smiles and turn it into something we can work with. We need to do that standardization and filtering step, and I haven't specified what these are yet. Maybe they're going to be different from context to context, and maybe we need some flexibility there. We need to generate a key or keys, do our duplicate checking and handling it however we're going to handle duplicates, and then store those. For lwreg, the standardization and filtering is configurable. So you can choose how you want to standardize molecules. You can choose if you want to remove H's or not. You can choose if you want to remove salts or not. You can choose if you want to neutralize or not. There's a bunch of built-in things. And if there's not something there that you want to do, If you have some other idea, it's really easy to just write a Python function to add a new standardization. Similarly, you can add a Python function to add a new filter. These can also all be chained together. So you can say, okay, I want to filter out polymers or molecules with overlapping atoms, and then I want to remove H's, and there's nothing really sensible to combine with this. Remove H's and then sanitize, do the standard RDK cleanup. So you can chain these to each other. The key piece of this is the key. So it's the registration hash. When the molecule comes in, what we're going to do is actually generate a number of hashes at a number of different levels of detail that allow us to answer the question, are these two molecules the same? Differently, depending upon what we care about. So the current layers that go into the molecular formula, because sometimes you just care about the molecular formula, right? If you're doing mass spec, maybe that's all you care about. It's there. I mean, I don't think it's really seriously going to be used to deduplicate molecules, but it's free, so we might as well include it. We include the smiles, canonical smiles, which is obviously that encodes a specific tautomer. We include the non-stereo smiles, which is a specific tautomer, but it ignores stereochemistry. So that allows me to say, I don't care about stereochemistry. Are these two molecules the same? We have a tautomer hash, which is a hash that removes tautomers, or that is tautomer insensitive. So I can have the same molecule in different tautomers. They give the same tautomer hash. There's the non-stereo tautomer hash, which I don't care about tautomers or stereo. It works. And then there's a couple of different things. So there's S group data, which is a standard S group. S groups are something you can have in mol files and P3000 mol files that allow you to attach extra data to the molecule. People often use this to do things like describe heteropisomers because it used to be, or it still is in most systems, hard to deal with heteropisomers. You can use that S group data to be used to deduplicate molecules. And then the last bit is some free text, which I'm happy to talk about later if you're curious about why that's there. And if you've ever written a registration system, you know why that's there. Here's an example. So here's the API for SMeprazole, or one of the ways of drawing it. And then these are the examples of the hash. So canonical smiles, we know. Formula, we know. No stereo smiles is just that with the stereochemistry removed. These are the tautomer hashes. The idea of the tautomer hash is something from Noel O'Boyle and Roger Sale. If you know Roger and have seen his code, these will look familiar. This is a very Roger type thing, the way these work. And it kind of looks like smiles and kind of not. And then for this one, there's no S group data, so that's empty. But this is what actually gets calculated at registration time and what gets stored in the system. You specify when you configure it, when you set up your system, what is used for deduplication. For at registration time, saying these two molecules are exactly the same, but all of the layers are stored, so you can always come back later and say, I have this compound, give me all of the tautomers of it, if you haven't done tautomer normalization when you register things, and I'll show you that. Okay, the last bit is conformers. So I mentioned that the way we're going to handle conformers is by hashing the atom positions. We do that really stupidly simple. So we don't need to worry about the connectivity. We don't need to worry about topology because that's handled by the registration hash. So all we need to worry about is where the atoms are, which makes the whole thing much, much simpler. So the way we do it is we take the atomic coordinates, we round them to 3 decimal places. You can configure that. We convert those into strings. We sort the atomic positions that are now strings, so we have them in a canonical order. We put them together into one flattened list, and then we calculate a hash on that, and that's the conformer hash. If I move any atom, the conformer hash changes. One thing we do not do by default is do any normalization of the tautomer. So if you have different orientations of exactly, sorry, I said tautomer, I meant conformer. If you have different orientations of the same conformer, they will hash differently by default. And the reason we do that is so if you're doing docking and you have different poses of the same conformer, you can deposit both of those in and have them by default not be duplicates. There is a built-in standardization option that will canonicalize the orientations for you. So if you don't care about the pose of the molecule, if you don't care about where it is in space and its orientation, you can standardize that. And this is just an illustration of that. So here's chloromethane. I apologize for the stupidly simple molecule, but I wanted it to actually fit on screen. We convert the positions into strings, we sort them, we flatten that into one big string, and then we calculate a hash of that. And this is the conformer hash for this molecule. So pretty easy. Now that we have a hash duplicate checking becomes really stupidly simple. It is a simple string comparison to check to see if we've seen a molecule or a conformer before, because all we have to do is say, is this hash in my database? What that gets you is you can have a database that has millions of rows, and all you have to do to see if you've seen the molecule before in those millions of rows is just do a string comparison. And any modern database can do that essentially instantly. So it takes, tens of milliseconds, maybe on a slow computer, to go through 2 million rows and say, have we seen this string? So duplicate checking is stupidly fast. This is the database schema. I'm not going to get into detail. I'm happy if you have questions, we can do it. But basically, there's a small number of tables. There's a table storing the details of the registration, how you're standardizing the molecules, what the RDKit version is, et cetera. There's a table storing the hashes. There's a table storing what you registered. So the structure that you gave it is stored in this table so that no matter, even if it's been standardized and changed, you can always get back to what it is that you put in. The standardized molecules are stored as mol blocks, and then if you're using conformers, those are stored in a separate table. Really simple. Here's a quick demo. I'm going to go very fast. This is setting up the system and initializing a new database. So there's a little bit of configuration information I provide. In this case, I'm doing the demo with SQLite, which is a database that doesn't require a server. It's built into Python. It's just going to use a file on disk. It's good for demos, but I wouldn't use it for real life unless you're not working with anybody else. There's nothing wrong with SQLite. It's a great database, but it's single user. That's the reason I say that. You initialize the database. This prompts you and makes you actually type in yes. So it used to be that this had an argument that said, yes, I'm sure, and it wouldn't do it unless you said, yes, I'm sure. But I had it happen a few too many times that I had in a notebook, lwreg.init yes, I'm sure equals true. And then came back later and re-executed the notebook and blew out my whole database. So now it makes you type something. So idiot-proofing. I start by registering some compounds. I have these 4 molecules. We have 2 things that are stereoisomers of each other, 2 different tautomers, and 1 molecule that's flat. I register those with there's just a call bulk register that you give a set of RDKit molecules to, or an SD file. And it registers and gives you back the IDs of those molecules. So this is a new database, so they're all unique. I get back 1, 2, 3, 4. I can query, so I can give it a smiles, an RDKit molecule, or an SD query. In this case, I'm querying for this smiles. That matches one of the molecules. It matches the first one, so it gets back. I can query and say, I don't care about stereo. So I say just query with the no stereo smiles. And now I get back 3 matches because I get back all the same things, all the same tautomers, but all of the stereoisomers of that tautomer. And the last one, I don't show it. I could also say no stereo tautomer, and then I would get back all 4 molecules. Once I have things that I found, I have those identifiers. I can then retrieve the structures by using the retrieve call. That's the API for lwreg. You can register, you can query, and you can retrieve. It doesn't, and you can blow up the database. That's important too. But it doesn't need to do anything else, and that's all it does. This is just showing how you work with conformers. In this case, I set up a configuration where I say I want to work with conformers. In this case, I am going to provide it 3D structures that I don't want it to mess with. I don't want it to remove hydrogens. I don't want it to standardize them. I just want it to take what I give it. And as is, so I turn standardization to none. Otherwise, this is all the same. The difference here is that when I register molecules, I get back 2 tuples. The first is the molecule registry number, and the second is the conformer ID. So now I have these 2 different things, right? So this particular topology, this molecule had 4 conformers, so I get back 4 entries, all with the same molreg node. And so when you're doing conformer mode, you get back the 2 tuple of molecule registry number and conformer ID. That's that. So I think we can probably wrap up. I'm happy to, I can talk forever. We have to be out here at 7. I thought it'd be nice to leave time for questions. So that's the repo. It has documentation. We have some tutorials and some demo notebooks in there. We're continuing to work on them. The tutorials include some examples of doing registration, but they also include some simple examples of working with experimental data, the stuff that Jessica talked about. We're trying to figure out useful ways to communicate how to do that, because I think that's the part that's, correct me if I'm wrong. The registration bit, probably most of you know about the idea of registration. Maybe the way I'm thinking about it is a little bit different. Maybe it's simpler than a real registration system, but that's not really new. I think the database bit is probably more new, the thinking about storing our results in a database and having it be easy to query. So we're trying to figure out how to make that more palatable and help people understand how to do it. So if you have suggestions, I'm happy to hear them. So thanks to Sarina. Of course, Paul and Mark were involved in a lot of the early discussions about setting these things up, particularly around the confirmers, because we took us a while to figure out how to make that work. And then Carl and Niels are more recent users who are doing it, and Niels has been contributing. Niels and Mark are sitting in the back. Obviously, the rest of the lab. I did a very early version of this talk that was 3 hours long. They asked me to do it. It wasn't me. I have all 150 slides at the end if you want me to keep talking. At this thing that Chris Steinbeck organized in Bulletin, that group we had a hackathon at the end, and that group did a lot of kind of helping with early versions of the code, as well as helping me think about how I communicate this. And then everyone else has contributed to lwreg. The last thing is an advertisement. So the ArcticKit user group meeting this year is in Zurich. We're hosting it at the ETH. It's from the 11th to 13th of September. It's free if you haven't been there. That's the registration link, which is awful. But if you Google, I'm trying not to say Google for things. If you do a web search using whatever monopolist you will, if you do it for 2024 ArcticKit UGN, you'll get to them. And I'd like to thank you for your attention, and we're both happy to take questions. And Jessica, you have to stand up again.